So this is the fifth video on chapter 14. It's going to focus on evaporation, boiling, and vapor pressure. So molecules on the surface of a liquid are held less tightly than those in the interior. So the most energetic among them can break away into the gas state in the process called evaporation. So you know how that molecules are held in the liquid state by intermolecular attractive forces. But the molecules on the surface experience attractions only to the molecules below them. So then they are held less tightly and will escape more easily if they have the energy to escape. The rate of vaporization increases with increasing surface area. So the more surface area, the more molecules are only held on one side and not above them, and then the more chances that they can escape. Increasing temperature, so the rate of vaporization will increase with increasing temperature because temperature gives kinetic energy to the molecule, and that energy can then be used to break away from the surface. The rate of vaporization increases with decreasing strength of intermolecular forces. So if the forces that are holding the molecules together in the liquid state, if they are not so strong, then the molecules will not need as much energy to break away from the surface. So all of this will help increase the vaporization. So some vocabulary here. Liquids that evaporate easily are termed volatile, while those that do not vaporize easily are termed non-volatile. Evaporation and condensation. Condensation is a physical change in which a substance is converted from its gaseous state to its liquid state. And evaporation and condensation are opposite processes. Evaporation is a liquid turning into a gas, and condensation is a gas turning into a liquid. And at the point where the rates of the condensation and the rate of the evaporation become equal, we have reached dynamic equilibrium. And the number of gaseous water molecules above the liquid will remain constant. The pressure that the vapor has when it is at equilibrium is called the vapor pressure. So let's look at this slide that illustrates what we just saw. So in figure A, we are pouring some water into a flask and putting a cap on it. And so now evaporation can begin. Evaporation is a surface phenomenon, so only the molecules at the surface will have enough energy to escape and get into the vapor phase. Now that we have some vapor above the liquid, condensation can also start and begins to occur. And when the rate of evaporation and the rate of condensation are equal, we have reached the dynamic equilibrium. Why is it called an equilibrium? It's because the rate of evaporation equals the rate of condensation, and we have reached an equilibrium in the sense that there is no more evaporation than condensation occurring. And it's dynamic because it's still happening. Evaporation is still happening, condensation is still happening. It's not always the same molecules that are in the vapor phase and in the liquid phase. So the vapor pressure increases with increasing temperature, because as you increase temperature, more molecules will have enough energy to escape. More temperature, higher temperature means higher energy, higher kinetic energy, and then enough energy to be able to escape the liquid phase. Vapor pressure increases also when the strength of the intermolecular forces that are holding the molecule together in the liquid phase, when those forces are decreasing, right? If you have weaker intermolecular forces, then it takes less energy to escape from the surface of the liquid and become vapor. However, vapor pressure is independent of the surface area. because an increase in surface area at equilibrium equally affects the rate of evaporation and the rate of condensation. So let's talk about boiling now. Evaporation only involves the surface of the liquid. It's only the surface molecules that escape into the gas phase. Boiling, on the contrary, involves the entire liquid. During boiling, all molecules have enough thermal energy to cause the molecules in the interior of the liquid to become gaseous. And so those that have enough energy will form bubbles that contain gaseous water molecules and that can escape from anywhere in the container. And we can see here from the beakers below that vapor pressure when you have only evaporation is much lower than the atmospheric pressure. So you cannot have bubbles forming. But when you have boiling happening, the vapor pressure above the liquid is equal to the atmospheric pressure, and that's what is defining boiling. Because when the vapor pressure of a liquid rises to a point where it becomes equal to the atmospheric pressure, that's when the liquid will begin to boil. So you know how Earth is surrounded by a layer of gas, and we call that layer of gas the atmosphere. It's mainly nitrogen and oxygen. And so here in the drawing, nitrogen are the diatomic blue molecules, and the oxygens are the diatomic red molecules. And so nitrogen and oxygens are matter, and they have a mass, and so they weigh on us. And so this is called the atmospheric pressure. And so when the vapor pressure of a liquid reaches the same value of the pressure of the atmosphere above it, that's when boiling occurs. And Seattle is very close to sea level. And so at Seattle, we usually see an atmospheric pressure close to 1 atmosphere. And so at 1 atmosphere of pressure, water will boil at 100 degrees Celsius. And we call the normal boiling points for substances at 1 atmosphere. However, if you were living in Denver, which is at 5,280 feet above the sea level, water boils at 95 degrees Celsius there. And it boils at a lower temperature because the atmospheric pressure is less when you are higher up in altitude. Because the air gets thinner as you move up in altitude. As you know, the matter made of nitrogen and oxygen gas settles down and due to gravity. And so as you move up into the atmosphere, the air gets thinner. You have less and less particles of air. And so this means a lower atmospheric pressure when you are on top of mountains. And so the water will boil at a lower temperature because pressure is less. And so that will reduce the temperature you need to reach for boiling. So how are vapor pressure and boiling point related? The vapor pressure of a liquid is affected by intermolecular forces. And if the intermolecular forces are holding the liquid together very strongly, the liquid will not be able to vaporize very easily, and its vapor pressure will be low. And it will require a lot of energy to break the intermolecular forces, and the boiling point of the substance will be high. So both vapor pressure and boiling point are dependent on the strength of the intermolecular attractive forces between the molecules that are acting to keep them in the liquid phase. And the stronger the intermolecular forces, the lower the vapor pressure, because it's harder to get into the vapor phase. And the higher the boiling point will be, because it takes more energy to get to the boiling point. So vapor pressure and boiling point are inversely related. Let's now watch a video on boiling water with ice.
Now we all know that if we want to boil water, we have to heat it up. That means 212 degrees Fahrenheit or 100 degrees Celsius. However, if you put water in a vacuum, we can boil it at a much lower temperature. So here's what we're gonna need. I grabbed an empty bottle, some oven mitts, a bowl of ice, and walked over to the sink. Now keep in mind when heating and cooling a glass object quickly, there's always a little bit of chance of danger. So put on some eye protection and be mindful. First thing you're gonna do is take your bottle and fill it about 1/3 of the way up with water. Then take it over to your stove. If you have an electric stove, put it right on there. If you have a gas stove like me, put a pan down first. Now you're gonna wait for the water to reach a decent boil. This may take a lot of time or it may take little time depending on how powerful your stove is. But once you have a decent boil, remove it with mitts and let it cool for about 10 seconds. Now it's time to put the cap back on the bottle and place it upside down. I happen to have a bigger bottle that I could place it into. Okay, so now we have some chilling water in a bottle. That's not very exciting, but this is where science steps back in. Now grab a couple ice cubes and place them on top of the upside down bottle. All of a sudden, we have boiling action. So why is this happening? Once we place ice around the water, it causes the vapor in the air to condense from a gaseous state to a liquid once again. This creates a vacuum around the water that's in the bottle. So now there's a lack of pressure above the water, which lets it boil again until the vapor cools down. Since we lowered the pressure above the water to nearly nothing, it now boils at around room temperature. This brings me to the bottom line. The water is boiling now because its boiling point has been lowered. If you enjoyed this segment, please check out some of our other videos. We have tons of cool science videos, or leave us a comment and let us know what you'd like to see on the next episode. See you then.
Let's look at the effect of polarity on boiling point and melting point. So melting point and boiling point, sorry. So in this table, we have three molecules, the methanol, the formaldehyde, and the ethane. We have their formula, and we have their molar mass. So let me show you how we calculate the molar mass. So to get the molar mass of compounds, you add the what is called here on the key, the average atomic mass of each atom that is part of the formula. So for example, in the molecules we have in the table, we have hydrogen. Its molar mass is 1.01, and so it's in units of grams per mole. It's the number below the name of the element. Carbon, if you look at carbon, its molar mass is 12.01 grams per mole. And then if you look at oxygen, it's 16 grams per mole. And so depending on the formula, you add them and you obtain the formula of the compound, or the molar mass of the compound in grams per mole. So here for methanol, you add 12.01 for one carbon, plus 4 times 1.01 for the 4 hydrogens, plus 1 times 16, and that's a total of 32 grams per mole for methanol. You do the same for formaldehyde, and the molar mass is 30 grams per mole, and for ethane, 2 times the molar mass of carbon plus 6 times the molar mass of hydrogen, and you get 30 grams per mole as well. So you can see that the molar masses are very close to each other. So it's we can consider that it's not a factor here. Now, if we look at the Lewis structures, starting with ethane at the bottom, there is only CC bonds and CH bonds. So we can tell that ethane is nonpolar. Formaldehyde is made of CH bonds and CO bond, and the CH bonds are not non-polar. The CO bond is polar. So as far as intermolecular attractive forces, we know that it will experience dipole-dipole attractions. Then methanol is made of CH bonds, which are non-polar, CO bond, which is polar, and the OH bond is also polar. So this is polar, and it's also able to have hydrogen bonding because hydrogen is bonded to oxygen. So the hydrogens of one molecule can be attracted to the oxygen of another molecule. So as far as intermolecular attractive forces, Ethane will only experience London dispersion forces because it's nonpolar. Formaldehyde will experience dipole-dipole attractions because it's polar. And methanol will experience dipole-dipole interactions and hydrogen bonding. So the strength of the forces increases from the bottom up for the molecules here. And so then now if we look at the boiling point of methanol is the highest. It's in the positive 60s. Formaldehyde has a negative boiling point, close to negative 20 degrees Celsius, and then ethane, negative 88, so much lower than the rest of them. So you can see that the boiling point increases as the strength of the intermolecular attractive forces increases. And so it's all the reason why you see this phenomenon of boiling point. For similar molecules that have similar molar mass, it's what will determine the boiling point is the strength of the intermolecular attractive forces. And so another example here with water. We know that water is experiencing hydrogen bonding in all kinds of directions because water is only made of OH bonds which are polar and which can experience hydrogen bonding. So water is held very strongly by hydrogen bonding. And so the normal boiling point of water is 100 degrees Celsius, which is even higher than the boiling point of methanol that we saw in the previous slide. And so it's remarkably high for a molecule with such a low molar mass. It's only 18.02 grams per mole. And the reason for this high boiling point is all these hydrogen bonds that water can form. And it keeps it in the liquid phase at room temperature, because other molecules with similar molar masses are typically gases, but not water because it experiences such strong intermolecular attractive forces thanks to the hydrogen bonding. And another thing here that you can observe with the noble gases, you can watch that their boiling points are increasing as you go down the periodic table from helium to neon to argon to krypton and xenon. We can see that the boiling point is increasing. And so how can the trend in boiling point can be explained for the noble gases? Well, again, it's all coming down to the intermolecular attractive forces. And here, noble gases are single atoms, free from each other, roaming around. And so, as you can see from the boiling points, they are all gases at room temperature. And to get them into the liquid phase, you need to go quite low in temperatures. And for helium, which is the smallest of the atoms, it's really, really low. And for xenon, it's higher. And you can see the trend that, going from the smaller atom to the bigger atom, the boiling point is increasing. And if we think about what noble gases are, they are nonpolar, they are single atoms, and the only intermolecular force that they experiment is the London dispersion. And so even though London dispersion forces are weak, here you can see how they affect the physical state of those gases, because bigger atoms experience stronger London dispersion forces, because bigger atoms, you can move their electron cloud more easily. They will have instantaneous dipoles more easily, and they can induce induce dipoles on neighboring atoms easily. And so the strength of the London dispersion forces in xenon is much higher than in krypton, which is much higher than in argon, than in neon or helium. And so you can see as the atoms get bigger that the boiling point increases, as well as the strength of the London dispersion forces. So now let's go through a concept check. So we have these four molecules: methane, formic acid, propane, and H2S. So we need to order them in order of increasing boiling point. So please pause the video to uh, uh, try to do this on your own before you watch the answer. And so let's find out the molar mass for each of these. And so again, for the molar mass, you use the periodic table and you use what is called the average atomic mass. It's the decimal number below the names. And so for methane, we have 1 carbon, 4 hydrogen, and its molar mass will be 16.05 grams per mole. Formic acid has a molar mass of 46.03 grams per mole, and propane 44.11 grams per mole, and H2S 34.09 grams per mole. So they have different molar masses. So we suspect that this will play a role in differing boiling points. Now let's look at the polarity of these molecules. Methane, made of carbon and hydrogens only, is nonpolar. Formic acid, looking at its Lewis structure, you can see that it's polar. The CO bond and the OH bonds are polar. Propane is nonpolar, only made of carbon and hydrogens. And H2S, sulfur has the same electronegativity as carbon, and it's only bonded to hydrogen, so it's also nonpolar. Now, if we look at the intermolecular attractive forces, so for each of them, we can list the London dispersion forces because all molecules experience London dispersion forces. And now, do they experience something else? Well, methane, no, because it's nonpolar. Propane, no, because it's nonpolar. And H2S, neither, because it's nonpolar. However, formic acid, being polar and having a hydrogen bonded to oxygen, experiences dipole-dipole interactions and hydrogen bonding. So very strong intermolecular attractive forces between molecules of formic acid compared to the others. So now, if we need to order them in order of increasing boiling point, we expect that the nonpolar molecules will be lower in boiling point. And here for them, the only difference is the molar mass. So the lighter one will be the one that is easiest to boil. So methane will be the lowest in boiling point. Then it's going to be H2S and then propane. And then we expect formic acid to have the highest boiling point of all.